In this section, we're going to take a look at another famous theorem that helps us compute the work line integral. So we're going to start with an example. We want to compute the work done by this vector field, where C is the piecewise smooth curve following the line segments from 0, 0, 0 to 1, 0, 0 to the point 1, 3, 3. So 1, 3, 3. And then 0, 3, 3. So 0, 3, up 3 units. And back to 0, 0, 0. So we're looking at something like this. We're going here to here to here and here. So I'll call this one C1, C2, C3, and the back one there, C4. Okay, so that's our curve. So piecewise smooth curve. These are just to measure 3 units up. Okay, just to give me a little depth perception there. In fact, I could even sort of put in something here just to give it a little more depth perception. Okay, so how are we going to do this problem? What options do we have? Well, one thing you might notice right away is that this is a closed curve. And we know that if we have a closed curve and our vector field is conservative, the answer is 0 because the potential function at the start and end point is the same. So maybe we'll get lucky here and figure out, is f conservative? So to check for conservative vector field in R3, we compute the curl of f and see whether or not it's 0. So go ahead and give that a try. By the way, there should be a comma here. So you can see I did not get the 0 vector. So f is not conservative. So then what options do we have? I would have to take this, and to get this work, I would have to break it down into the piecewise smooth curves. I'd have to break it down into C1 and C2, C3 and C4. Now, it'd be a good practice for you to do that. It's just line segments, so you're parameterizing those line segments and working in there. So you might want to try that. It's easy enough to do, but it is a little tedious. So what we're going to do is look at another way to do this. But I'm going to start with a real quick review of line integrals. So when we talk about line integral with respect to arc length, that's the first one we talked about. That was in the first part of 16.2, and that was where we had an integral over a curve, either for a function of 2 variables or a function of 3 variables. That wasn't the work line integral. There was no vector field around in this case. What we did is we replaced ds with magnitude of r prime of t dt, and we put in for x and y and z our parameterization of our curve. So we got that all in terms of t. Okay, then we brought in a vector field. And when we bring in a vector field, if we compute the integral of f dotted with the unit tangent ds, so we compute this line integral with respect to arc length. Our function is f dot t. We found that the shortcut way to do that is to take f, put f in terms of t, and dot it with r prime. That's what I mean when I say we're going to do this directly. We then went on to find in section 16.3 that if f, the vector field, is conservative, we have more options. So if f is conservative, which, by the way, how would we know? We either have the mixed partials equal, where the partials are continuous on some simply connected open region, all that extra part, right? Or if the curl equals 0, if we're in R3. So if f is conservative, that gave us options. We could use the fundamental theorem, which would require us finding the potential function, f, and then just taking f of the endpoint minus f of the start point. The other option we have, if f is conservative, is we can choose a simpler path. We then went on to learn that we have another option if the curve is closed and we are in R2 and the curve is positively oriented. That was Green's theorem. That was section 16.4, which said that we can compute the work by doing the double integral of the partial of q with respect to x minus partial of p with respect to y as a double integral integrated over the region enclosed by the curve, right? So that problem that we just looked at on the last slide, I said we could do it directly. That wouldn't be too hard, but it'd be a little tedious. If f is conservative, we would have options, but we found out it's not. If C is closed, well, our curve was closed, but R2, Green's theorem only applies to R2. We're in R3. Well, it turns out there is a theorem for a closed curve in R3, and that's what we're going to look at in this video. So here is the theorem. This is actually an extension of Green's theorem. Green's theorem is a special case of this. And I'm not going to go into a proof. There's a partial proof in the book. I'll give you a little bit of an idea of maybe why it works. But this is called Stokes' theorem. And here's the way it works. It says, let S be an oriented surface. Okay, so a surface, first of all, what does that have to do with a line integral? We're talking about trying to find a line integral, and we have a three-dimensional surface. So let me just draw in some sort of, that doesn't look very three-dimensional, but suppose that's some three-dimensional closed curve, okay? And S is a surface bounded by a simple closed piecewise smooth boundary curve C with positive orientation. Okay, that's a lot to take in. So here's our C. And S is a surface that is bound by this curve. So for instance, if I make a surface here, whose edges are that curve. Okay. Now that surface is oriented. So suppose, for instance, we have positive orientation, so an upward unit normal on our surface. A curve having positive orientation, not as simple as counterclockwise. How does that work? If you walk along this curve and your head is in the direction of the orientation of your surface, so in the picture I have, it would be upward. Positive orientation would mean that as I walk along this surface with my head pointing in this direction, that the surface will always be on my left. So in this picture here, that would be a positive orientation for that curve. Looking down on it, it looks like it's counterclockwise, but that description is not going to be very good when this curve starts getting real crazy. So for positive orientation, the orientation of the curve has to match the orientation of the surface. Walk along the curve, your head is in that direction, surface is on your left. Okay, so we've got the first part of this figured out. Now, F is a vector field whose components have continuous partial derivatives. This work integral, that's what we want. Okay, according to Stokes' theorem, another way of computing this is to compute the surface integral. So we want the integral around this curve. And we're going to get it by computing the surface integral of this green surface. But we're not computing the surface integral of f. We're going to compute the surface integral of the curl of f. That's important because sometimes I forget I've got to take the curl. And how do we compute that? So let's think back to how we did the last section. The shortcut for computing this surface integral is to take that vector field. And by the vector field, I mean that vector field there, the curl vector field, and we dot it with gradient of g dA, and that's now a double integral. Where specifically g was whatever our surface is, getting everything on one side, that was our g. Coefficient of z is 1. Now, one comment that I want to make is that this surface is any surface that's bound by that curve. I just kind of drew in a surface, kind of a minimal surface, but any surface that's bound by this curve. What I mean by that, the example that I can give you, if you ever played with those bubble wands as a kid, where you put the little wand into the bubbles and pull it out and blow it. Suppose this was a wire. This was our wire that we were going to dump into our soap solution. As it comes out, we would get this, what we call minimal surface. But if I started blowing on it in either direction, suppose I started blowing on it that way, I would get some sort of surface that maybe was more rounded. You know, use your imagination there. So I might get some sort of surface that's more of a bubble instead of something flat. I could use that surface instead. So this surface that is bound by the curve, there are infinitely many surfaces that are bound by that curve. There are infinitely many that we could use. So we'll do an example shortly where you see what I mean by that. But let's go back to the example that we did previously, and then we'll come back and talk about physically why this seems reasonable that this would be the case. Okay, in our example, our curve went from the origin, out 1 unit, up, over, and down. So it's a closed curve. If you look down from above, it is counterclockwise. What surface is there? Well, any surface that is bound by, again, think of this as a wire here, any surface that's bound by it. So any sort of surface that you could blow with your bubble solution. In this case, this minimal surface, this flat surface, this all lies in a plane. And the way you can tell that is because of these points. These are both where z equals 3, z equals 0. Both of these points have the same y value of 3, and so on. So you could find that the equation of this surface here is z equals y. So according to Stokes' theorem, if I want the work line integral, I can do the surface integral of the curl of f dot ds. And remember, our surface integrals we do like so. Okay, so we need all the pieces of that. The curl I found on the first slide is 2xy negative y squared 4y cubed. We would put our surface in here. Our surface is z equals y, so z is the dependent variable. And there's no z's in here. If there were, we would put a y in for the z. What is our g? Our surface is z equals y, which I can write as z minus y equals 0. And so this is our capital G. We take the gradient of that, and we get 0, negative 1, 1. That would give us an upward orientation, which matches with the idea of that positive curve. If I was walking along this curve in this direction, with my head in that direction, the surface would be on our left. So it is. The direction that I was given was to go around this way. So then we take the dot product. And we get y squared plus 4y cubed. So that gives me this double integral. Now what is the d? D would be the projection down here. And so that, what is that? X goes out to 1 and y goes to 3. X goes out to 1, y goes to 3, so just rectangular. Okay, so simple enough integral at this point. I think that you can work that out. Intuitive idea of why Stokes' theorem might work. Again, you prove it in an advanced calculus class, but just to get a little physical idea. We're trying to compute the work done by a vector field in moving an object around a curve. So this was the example that we had, and this is a picture of the vector field. So this orange was our vector field that was given in that example. Now on the right, what you see is the curl vector field. Remember in the video that I did about divergence and curl, the curl measures the propensity of this to to swirl around, if you will. At any given point, the curl will be a vector having to do with how much this is swirling around. So at any given point, here would be the curl at that point. So you can see that the curl vectors are short here, they're getting bigger here, and roughly the idea is we've got this sort of swirling action going on here a little bit, and more so here. It's hard to tell with this vector field, but that's what's going on. And these are pointing upward, which means the swirl is going in this positive direction. Okay, so why might the work done in moving an object around this curve be related to the flux? This is the flux of this vector field across this surface. Well, you can kind of see it. The more that this vector field is curving around, in this case, it's helping us around this curve, its curl vectors are going to be bigger this way, which means the flux is going to be bigger. The more this is swirling, the more that the vector field is increasing the work done on this by the vector field in moving the object around, the more flux that there's going to be across this surface. So that's a really rough idea. There is a resource in the module, it's a Khan Academy video where he does a really good job kind of walking through the idea of why these are related, if you're interested in learning more.